So what we're going to do in this video is look at some interesting fermion and boson interactions, and we are going to apply some conservation rules. Now, I'm going to give you some examples of some situations where fermions become bosons or the other way around. The most common is the annihilation reaction, which is a positron. Is an example of which is if a positron meets an electron. Now, this is the antimatter equivalent of an electron. So when they meet, they poof disappear. Well, they don't actually. They don't disappear. They interact in such a way that the mass becomes energy. And yes, that involves Einstein's equation, E equals mc squared. So the mass equivalence of these two particles meeting will then be manifested as energy in the form of photons. Now, similarly, the opposite can happen. We can have a force particle, such as a photon, becoming suddenly, just like that, a matter-antimatter particle pair. So this is a pair production, when a photon magically becomes two particles, a beta positive and a beta negative. Now, as you can probably imagine, there's some maths associated with this. Calculate the wavelengths of the released photons in this situation when an electron and positron annihilate. Step 1 is to find the energy equivalence of these two masses. Now, this has been done for you. You can see the energy equivalence of this particle here and this particle here. So now, if you know what the total energy is, how can you find the wavelength? Okay, and so you know that HF equals energy, but the frequency is not what we're looking for. We're looking for wavelength. So wavelength would be the speed of light divided by the frequency. So wavelength equals Planck's constant times the speed of light divided by the energy. You should get 2.4 times 10 to the minus 12. If you don't understand what's just happened here, stop and call me over. Now, that's only two interactions that we can come across when we're looking at matter and force carrier interaction. The actual number of interactions that can actually happen is huge, and so when things like particle colliders are used to analyze these kinds of interactions, sometimes it's a little bit like a jigsaw puzzle. You have to kind of like piece together the information that's being read and hypothesize certain interactions. The best way to check that those interactions are even possible is to use conservation rules. So even though we are dealing with the crazy world of quantum particles, rules do apply. And so the conservation laws must be applicable to every interaction. And there are 4 very important laws. The first one is the quantum number for charge is always conserved. So what does that mean? For any interaction, and these two are just some random interactions, right? A proton and a neutron become a proton, and the pion. This is another one. A pion plus a proton becomes a neutron and another pion. So all of these are possible interactions. So what we have to do is check that they apply or they follow conservation rules. So quantum number for charge is always conserved. So is the charge on this side equal to the charge on that side? Is the charge on this side equal to the charge on that side, right? The quantum baryon number is always conserved. So you would need to check that both sides of the equation have the same baryon number. The lepton number has to be conserved. So you have to make sure that both sides of the equation have the same lepton number. And strangeness is conserved. So you have to make sure that the same number of strangeness is on both sides of the equation. So that's what we're going to do now. We're going to check the conservation laws apply in order to see if an interaction is possible. So let's have a look at some examples. Here we have a neutron becoming a proton and an electron and a neutrino, right? So we have to see if the conservation laws apply. So let's have a look. The baryon number, a neutron has a baryon number of 1. Right? On this side, a proton number has a baryon number of 1. An electron has no baryon number and a neutrino has no baryon number. So the baryon number is conserved. Let's have a look at the lepton number. We have no leptons here, so the lepton number is 0. The lepton number here is a 0. The lepton number here on an electron is 1. But here we have an antineutrino. An antineutrino has the opposite lepton number to a neutrino. So it has a -1. So we can see here that the lepton numbers are conserved. So let's have a look at charge. Charge on a neutron is 0. The charge on a proton is 1+. The charge on an electron is -1. And the charge on an antineutrino is 0. So we have the same charge on both sides. Strangeness. There is no strangeness here. So therefore we have a 0 strangeness on this side and 0 strangeness for all of these because there are no strange quarks involved here. So we have strangeness 0. That means that this interaction shows conservation and is possible. Let's try the next one. Now, what is this particle? This is a K0, and in order to proceed, we're going to have to figure out what this is. So if we look on our list of mesons, because that's what this is, a K0 is a meson which has a down quark and an anti-strange quark. Okay, this is getting messy. So on this side, we have, and let's start with baryon number. The baryon number is 0 because this is a meson. Now, what are these particles? They look like pions. So if you have a look here, pi plus and pi minus, these are indeed mesons, and they have, again, a baryon number of 0. So that works out. Leptons, there are no leptons here at all. So the lepton number will be 0 on both sides. And let's have a look at charge. Now, the charge on one of these K particles, K0, is 0. And the pi plus and pi 0, they have a, let's have a look. We want a K plus, which has a charge of +1, and a pi minus, which has a charge of -1. So these balance, okay? We have balanced charge here. Now, strangeness. Strange is involved here. The K0 has a strange antiquark or an anti-strange quark, which means it has a +1 strange value. But if we have a look at pi plus has no strange particles and pi minus has no strangeness. So therefore, this is not conserved, and so this interaction cannot occur. I hope this makes sense and you know how to apply the conservation rules.